Welcome Year 11s to this lesson on moments and levers. Now if you need to pause the video at any point during this presentation, do so. In this case you might want to do so to write down the title. Give me a lever and a place to stand, and I shall move the earth. This is a quote by an ancient Greek named Archimedes, who discovered that levers had the ability to amplify the force provided by a human. We use levers every day, whether we're tightening a nut with a wrench, whether we're moving a heavy load with a wheelbarrow, or just opening a door. You may have noticed that it's easier to open a door when you push the side far away from the hinge, but very difficult to open the door if you push it from next to the hinge. Levers are used thanks to this observation, that the further you are from the pivot, the longer you'll have to push, but the less force you will have to use. This allows us, with our limited strength, to apply forces far beyond that of any normal human. A lever consists of three important features. The load, that's the force that's needed, such as the weight you want to lift. The pivot, that's the point about which you are trying to turn, like the center of a circle. And the effort, that's how much force you will need to apply to lift that object. What allows a lever to do its job is when the distance from the load and the pivot and the distance from the effort and the pivot are different. So for example, if we move this load so that it is halfway to the pivot, meanwhile we keep the effort at the same distance to the pivot, we find that the effort you need is half that of what it would have been. So because the load is half the distance to the pivot, the effort can be half as much. So a moment is the turning effect of a force. Now, if you think about the example we just gave, you notice that there must be a mathematical relationship between these numbers. In fact, we define a moment as the product of the force and the perpendicular distance to the pivot. So a moment is the turning effect of a force, but mathematically it's when you multiply the force you've applied by the distance between that force and the pivot. Now let's look at what we mean by the word perpendicular. So we'll take a wrench. Imagine that this wrench is 0.23 meters between the center of the pivot, which is the center of the nut, and the location where you're going to push with a force of 100 newtons. If we look at the moment, the turning effect of this force, first of all we write our equation. Moment equals force times perpendicular distance to the pivot. Then we substitute in the numbers. Instead of F, we're going to write 100, and instead of D, we're going to write 0.23. When we multiply these numbers together, we get that in this case, the turning effect is 23 Newton meters. However, once the wrench has started to move, the perpendicular distance from the force to the pivot have now changed. Notice that even though the wrench is still the same length, the distance between the force and the pivot is now only 0.22 meters. As a result, we can write our equation again, replace F with 100, replace D with 0.22, and we find that this time we've only got 22 Newton meters. Finally, let's do that again, but at a much greater angle. You see now there is only 0.19 meters from force to pivot, but still 100 newtons. This means that the turning effect of the force is reduced as the wrench is turned. This gives us 19 Newton meters. If we consider a wheelbarrow, let's look at how this is the same as a lever. First of all, we have our pivot. That's at the base of the wheel. Then we have a load, and we have its perpendicular distance to the pivot. And we also have our effort, which also has its own perpendicular distance to the pivot. So we can work out how much effort is needed if we are given the load and the distances to the pivot from the load and the effort. So let's use this example. In this case, we have a load of 200 newtons. We have its distance to the pivot is 0.3 meters. And then we have an effort that we want to find out, but it is at a distance of 1.2 meters from the pivot. So let's solve this problem. The turning effect of the force is the product of these two numbers. So we'll start with the equation. The moment equals the force times perpendicular distance to the pivot. In this case, we're going to take the load and its distance from the pivot. So we've got 200 times by 0.3. And this gives us a turning effect of 60 Newton meters. Now that means in order to lift this, the effort required is going to have to produce 60 Newton meters of turning effect. So the moment provided by lifting it will have to be equal to the moment of the load. That means we write our equation again. We can replace m for moment with 60, and its perpendicular distance between the pivot and load and effort is 1.2. Once you've replaced those numbers, you can make F the subject of the formula, and you find that 60 divided by 1.2, that is 50 newtons. So even though the wheelbarrow contains 200 newtons of weight, you only need to provide an effort of 50 newtons. Finally, we'll look at a seesaw. In this case, we want to find out again the effort required to lift, or at least balance, this load. Now, I've used the word equilibrium here. What that means is this is perfectly balanced, that the seesaw is neither tipping nor rising. So we start off with the anti-clockwise moment. So if you look at the pivot in the center, you think, how is that weight, that large orange circle, how is that going to move the seesaw? Well, it's going to turn that seesaw anti-clockwise. And so we find our anti-clockwise moment first. We write the equation. Then we replace F with 450 and D with 0.7. This gives us a turning effect of 315 Newton meters. Now, in order to balance that, the effort must also result in a clockwise moment of 315 Newton meters. So what we'll do now is we'll write down clockwise moment. We're going to write our equation, and we know that this moment, in order to balance it, if it's in equilibrium, it must be 315 Newton meters. So we write 315 equals F, which is our effort, times by 2.1, which is the distance between the pivot and the effort. We rearrange the equation to make F the subject of the formula, and we find that the total effort is 150 newtons. So even though the load is 450 newtons, we only need to apply an effort of 150 newtons to balance it. If you look at the numbers themselves, you'll notice that the load is 3 times closer to the pivot, and so therefore the effort can be 3 times lower. What follows in the next section is a set of questions for you to complete. Pause the video for every question you see and complete these in your exercise books or on paper.